Welcome to a special edition of ChemVid. Today we're going to finish the nuclear chemistry notes. So last time you were asked to write the nuclear equation for the alpha decay of polonium. If you wrote the correct equation, it should look something like this. Lead has an atomic number of 82, so 82 plus 2 is 84, which equals poloniums, and then 208 plus 4 equals 212. Now what I want you to try to do is I want you to try to solve the next two questions, the beta decay of iodine and which element undergoes alpha decay to form lead 208. Give that a try. Is this what you got? Good. If not, let's go over it. So iodine is number 53 on the periodic table with a mass of 131. A beta particle looks like this. Or you could have written it out as this. Either one will work. Then, since beta is a negative 1, I need to have an atomic number higher than 1, so that when I take 54 plus a negative 1, I get 53. Then, my protons and neutrons shouldn't change because there's no change in a beta particle, so therefore I have the same mass. As for the next problem, you are supposed to find out which particle it would take in order to have alpha decay and form lead. Well, ta-da! Here it is. If you have alpha decay, that's this, and it forms lead, 82, then you needed to start off with polonium. Before we move on, I'd like you to go to your nuclear equations worksheet. If you don't have that, you can find that in Canvas under your assignments. And I wanted to go over another example that uses a little different wording. This one is talking about aluminum 27 is bombarded with an alpha particle. So the first thing I need to do is I need to start off with aluminum 27. I look on the periodic table and aluminum is number 13. Then it says is bombarded with. Bombarded means that I am adding this particle. So I'm adding an alpha particle to the aluminum. I'm going to hit it with enough alpha particles until it reacts to form phosphorus 30. And if I look at the periodic table, phosphorus is number 15. And one other particle is produced. What is the nuclear equation for this reaction? So I've got it started now, but I'm looking for this extra particle. 13 plus 2 is 15. Well, I have a 15 here, so whatever it is, it has to have a 0 here. 27 plus 4 is 31. I have a 30 here, so I need a 1 over here. 1 plus 30 is 31, so now they're the same. So what has 1 mass number but 0 protons? The answer is a neutron. So when you take aluminum and you bombard it with helium, it creates phosphorus and a neutron. Okay, now that you know how to write these nuclear equations, keep practicing of course, but we're going to go and we're going to look at some of the negative and positive effects of radiation. For a lot of people, radiation brings up a negative connotation. Atomic bombs, poisoning, Chernobyl. If you don't know what Chernobyl is, Google it. It was a horrible thing that happened. Maybe even the dentist, because they use X-rays or beta rays to take X-rays of your teeth. So sometimes we just focus on the negative. Lots of negative effects of radiation. But there are some positive things. For instance, power is a really nice thing that we have. In France, 75% of their power is from nuclear energy. The United States only has 19.9%. Is this good or is this bad? That's an opinion question that you can decide later. But nuclear energy is very useful. It's very cheap because it's not as expensive to buy the rods for as much electricity that is produced. However, there is nuclear waste, right? So you have to look at the pros and the cons. But a positive effect of radiation is we can get energy from it, and it's cheap energy, and it's good energy. A nuclear power plant runs by putting rods into a container. These rods are usually uranium, and as uranium decomposes, as it undergoes nuclear fission, the energy let off from that flows into a container that has water. The water turns into steam, and then the steam turns the turbine. We can then collect the electricity as that turbine moves. Then all the extra steam that comes through is cooled using water, and then can go back and be reused. So this is very good because it's a circular event. Not a lot of energy is lost, and it's rather cheap. The only problem is that once you have these rods and they've undergone enough radiation that they are no longer useful, then we have to get rid of these rods, which takes some time and a lot of digging. All right, mostly in like Nevada and the desert. But nuclear radiation is useful for energy. Another thing that is good for is imaging. When you go to the doctor, they might ask you to swallow a small amount of radioactive substance. TCM-99 is a big one. And what it does is it makes your innards glow so they can see if you have a tumor or if you have a lump in your throat or in your body somewhere. So it's actually very good at that. Another thing we use it for is food irradiation. So I bet you didn't know this, but your food that comes from the farm, a lot of it is put into the path of cobalt or cesium. And these gamma rays go, and what they do is they kill all of the bacteria, but they leave the food unharmed. So then we can eat the food, and it gets rid of the bacteria for us. Irradiated milk, this allows us to have a longer shelf life because it gets rid of the bacteria without harming the substance. So there are a lot of positive effects of radiations, a lot of positive uses. However, there are negative effects. So cancer is one of the biggest things people think of when they think of negative effects. When you're exposed to radiation, you can get cancer. And as you notice, as the dosage of radiation goes up, it gets worse. So, death is bad, yes, and it can happen if you get exposed to too much radiation. However, we do get exposed to radiation every single day. The sun gives us radiation. There's geothermal radiation, which means radiation from the earth. But it has no observed effect because it's not enough to hurt us. If you get slightly more, you can get a decrease in white blood cell, which leads into a poor immune system, which leads to loss of hair, nausea, and then hemorrhaging or bleeding internally. This may seem familiar. Cancer treatment is when they irradiate your skin or, well, your cells, and what they're trying to do is they're trying to kill the bad cells, the cancer cells, and hopefully your healthy cells are strong enough to be weakened, but then come back after the cancer is dead. So, negative effects of radiation, death, cancer, those types of things. But we also use radiation to help cure cancer. Let's see, some other things. Let's see. So these are all of the ways that we can get radiation. We also use radiation in x-rays, radiotherapy, and internal diagnosis. That's what we were talking about before. Nuclear power plants, TVs, you guys like that? Some negative effects, however, when a nuclear power plant goes down, it can create cry to stir. Look up Chernobyl if you want to. So negative effects, we got cancer. It's used in war, which could be either a good or a bad thing, depending on your point of view. But there are two sides to radiation, just like everything else. All right, let's move on and talk about half-life. All right, so you have two vocabulary words here, half-life and radionuclide. please read the book description or the book definition that I have put there, and then write it in your own words. You may think this is a silly thing and you're just going to wait for me to explain it anyway, but being able to read, condense information, and turn it into your own words is a great way to be able to learn new things. Not just chemistry, but anything. So please take the time to try to write these in your own words before I go over them. Alright, hopefully you did that. So a half-life is the time it takes for half of a radioactive substance to decay. So for instance, if I started off with 10 grams of a radioactive substance like uranium, and uranium's half-life, or T half, is equal to 2 days. I'm not sure about that. I'm just using this as an example. But if it's 2 days, after 2 days, only half of my substance will be left, 5 grams. After 2 more days, only 2.5 grams will be left, because that's half of 5. And then after 2 more days, it'll be 1.25 grams, because that's half of 2.5. So half-life is how we measure how fast a radioactive substance goes away or decomposes. So what you do is you take your total, divide it by half, then divide by half again, then divide by half again, then divide by half again. And that's how half-life works. And once you get to a certain amount of radioactive substance left over, then you can know if it's dangerous or not. So when we're digging up and we're putting nuclear waste in Nevada or wherever we do it, it's to wait until it decomposes enough that it's no longer dangerous. So now let's talk about a radionuclide. A radionuclide is the particle that comes off of the radioactive atom. So this is my radioactive atom. It looks like an egg, but it's radioactive. Radioactive atoms let off smaller particles, right? Smaller nuclei, like alpha particles or beta particles or whatever. So a radionuclide is referring to whatever the radioactive atom gives off. Alright, let's try an equation. So the half-life can be measured using this equation, with the variables listed here. So if I want to know how much of my substance will remain after 19.25 days, the first thing I have to do is I have to look for my variables. Pause the video for a moment and see if you can identify which variables we have and which numbers they go with. Did you get it? So N naught is the initial amount, which they told me here, the initial mass. N is how much is left over, or the final amount, which is what I'm looking for. 19.25 days is how long my decay will happen. And then T half is the half-life. So now all I have to do is plug it into my equation. Okay, so N is what I'm looking for. 198.72 goes here. And then I put my T and my T half up here. Now, the most important part of this is order of operations. So the first thing you need to do is you need to take T and T half and divide it. That's the first thing you should do. The next thing, you take that answer and you raise 1/2 to that answer. That's the second thing you should do. And then the third thing you should do is you should take whatever that answer was and multiply it by 198.72. Order of operations makes a big difference in this one. What do you get when you plug that into your calculator? If you got 6.04 grams, you did it correctly. If not, make sure you're plugging it into your calculator properly. Okay, time for an assignment. Before you come to class, try problem number 2 and get the answer. And then for problem 3, set it up. You might need a little help with the math because it does require a little bit of finagling with the algebra. But at least set up number 3. Good luck!